So today in our talk I would like to motivate a little bit how visualization can help to access the quality of subspace clusterings. So in my research I'm dealing with a subspace clustering. So experiments have been shown that the application of full space clustering, considering the full set of all dimensions of a large data set, is usually does usually not provide very good results if you have a large number of dimensions. The reason for this is the so-called curse of dimensionality. So on the one hand, with a large number of dimensions, you typically have a large set of noise and non-relevant dimensions in the data. But more importantly, the objects in our data set are usually not similar to each other in all aspects of their dimensions. So what we can easily see in the example above, that we can cluster these high-dimensional data, high-dimensional just in quotes, either by their color or by their shape, and we get two different clustering results, but they are both valid. We see a more realistic example on the right side where we have demographic data and we want to cluster it, and we see that we get two completely different clusters. So on the one hand, if we cluster our data based on income and traveling frequency, and we get we have the same clusters, the same objects in a completely different result if we analyze it based on age and the blood pressure, for example. So it's very simple to see that there are at least there are a lot of different possibilities to cluster the data. These examples here are rather easy to get an intuition, but in real-world examples, we usually face the challenge that we don't know which subspace are relevant to search for our clusters. So generally, the aim of subspace clustering is to search for different clusters in lower dimensional projections of the data, and hereby to simultaneously search for which subspace is considered relevant and to find in each subspace the respective clusters. So there is an exponential number of potentially interesting subspaces, so we need efficient methods to search through the whole search space to find the relevant and interesting subspaces. Independent of how efficient or effective these methods are, we have the major challenge in subspace clustering, which is called redundancy. So we can have clusters in one subspace, different clusters, which is kind of additional information, but we can also have similar clusters in completely different subspaces, or we can find similar clusters in similar subspaces. While the first aspect gives us additional information of our data, the second and the third aspect is some kind of redundancy information which is encoded in more than one cluster, which should be avoided when we apply a subspace clustering. We already know from full space clustering that it is very challenging to evaluate and that there is not a single quality measure to say how good a clustering result is. Due to the different clustering methodologies like partitioning-based and density-based clustering. The question is now, how can we evaluate subspace clustering if we already know that full space clustering is quite challenging, and now we have additionally the subspace information given. So in our paper, we propose to use visualization as one mean to assess the quality of subspace clustering. And therefore, in our paper, we give first a comprehensive overview about what are the quality criteria for subspace clustering. So what should we consider? And secondly, we provide visualizations to support the quality assessment of the subspace clustering. And hereby, we do not focusing on hard numbers to say like this clustering is that much better than the other clustering, but we want to give reasons and insights. What are the reasons for a good clustering and what are the reasons for a bad clustering, so that the algorithm designer can change the parameters or adjust, or use a different clustering algorithm. So we implemented our visualizations into a common framework, which you can try out online. And you can also register and upload your own clustering results if you like to. The intended users and applications for our tool are either algorithm designers who develop novel algorithms and want to compare their original intentions to the output of the algorithm, or users who want to apply clustering algorithms to unknown data. the goal of that project or that framework is not to extract knowledge of the detected clusters in yet, but purely on assessing whether the clustering result makes sense or not. If we go for the related work, there are basically 3 different approaches to assess the quality of clusterings and subspace clustering. First is we compare our clustering result with some ground truth information and decide how well that fits together. The second aspect is the internal evaluation, purely based on clustering characteristics, so for example, density or separability, but that is, so far there are no quality measures, internal quality measures for subspace clustering given in the literature. And finally, we have the evaluation based on domain experts of the underlying data, so we provide the clustering result to a domain expert who knows the data and can tell whether clustering makes sense or not. Once again, our tool focusing on insights given for a good and bad performance, and an all-embracing view on the clustering result, and no hard numbers or no quality aggregation of different quality measures. So let's look into the general idea. So redundancy in subspace clustering is highly correlated with similarity, as highly similar result provides some kind of redundant information. So what we can do is we can compute the similarity of our subspace clusters based on the object similarity, so whether 2 clusters are actually similar, or based on the subspace information, whether 2 subspace clusters share a lot of different dimensions. So we can compute this with some set-oriented techniques like a Jacquard index or overlap index, and then compute a similarity matrix, use any kind of distance-preserving projection, for example, multidimensional scaling, and we result in a plot like this, where nearby clusters are, or where similar clusters are encoded by nearby points. So we can see here that we have quite a few clusters which are similar based on the object similarity over here, and quite a few which are similar based on the subspace information. The question is, how can we combine these 2 informations, as clusters are only truly redundant if they are similar in their object and in their cluster member, in their subspace information. So our idea is basically to first compute the projection based on the subspace similarity and object similarity separately, and then we map the points on top of a 2D color map, which is perceptually linear, and then extract the colors from the color map. So far, we have similarity now encoded with nearby location and additionally with the similar colors. In the next step, we project the colors on top of the MDS projection from the other similarity, in this case, object similarity. So we have now the original projection, or the location is based on the object similarity, and the similarity based on the subspace is given by the coloring. We can do this the same for the object similarity way, and we have in the end these 2 interlinked MDS plots, which combines both similarities together. So how can we interpret now this plot? So nearby clusters in the object similarity plot can either have the same color, which means that the cluster are now similar in the object space and in the subspace space, or they can have different colors, like over here, so they have the same or similar clustering structures, but in completely different subspaces. In the following, we map the size of the clusters additionally to the size of the object similarity plot and the size of the subspace to the plot on the right side. So in our paper, we provide some kind of a lookup table to the most commonly patterns and how we should interpret them. And we just look into some of them. So first, here's an example for high redundancy. So we see that we have a lot of clusters here which have a similar color. So they are more or less the same clusters. And the guess could be that the redundancy elimination strategy of a subspace clustering algorithm didn't work here so good. On the other hand, we have here an example with low redundancy. So we have, again, some kind of groups of similar clusters, but they occur in completely different subspaces. We can also look at information like cluster split-ups in subspaces. So we can see here that we have quite a few clusters which are completely similar, but they occurring in different subspaces. So an analyst could now guess that the objects itself here should form a unified cluster in a more higher dimensional space. I brought here some examples for good and bad clustering results. So we can here quickly see that we get a lot of clusterings of different sizes. They are usually not overlapping, so they have a different topology in their object and similarity space. And on the bottom we can also see that we get here some clusters which are rather large with the same color, so different clusters in different subspaces. We can also see examples like this, where we get a lot of very small clusters down here, or groups of clusters with the same color, which actually encode a lot of redundancy, and the user should refine the parameter settings. Or examples like this, where most of the clusters are actually similar. Same as here, we have basically too much subspace clusters, a lot of redundancy encoded, or down here, where most of the clusters are actually the same. When we assess the quality criteria of subspace clustering, we should not only concentrate on the non-redundancy requirement on the plot which we have seen so far, but more in our tool we also encoded meta visualizations to now select certain clusters and visualize them with more detailed visualizations. So for example, with a visualization which is called class nails down here, where we provide the possibility to compare the clustering topology of the individual clusters. We also look at object and dimension coverage criteria. So for example, a useful clustering should consider most of their members in any kind of cluster. But for subspace clustering, we should also concentrate on whether all dimensions are part of any subspace to reason about the whole data set. So we can do this with simple bar charts, and we can also access different cluster characteristics itself with, for example, distribution chart to see what is the distribution of my clustering. So I have a lot of large clusters or small clusters. Do this actually make sense? And finally, if we have seen that the clustering itself has a nice structure, we should analyze the clustering itself. So here on the right side we see an extended parallel coordinates plot where every dimension is represented by one bar, and we have this heat map in the background showing the data distribution of the whole data set. And now we basically connect all the members of one selected cluster with one of these lines, and can see that and can also see the highlighted bars are part of the subspace of that cluster. So we can see in the example above here that most of our cluster members are actually very compact, so the cluster itself makes sense. But an analyst might question, why is the dimension 0, 2, 3, and 7 not part of my subspace cluster? So, so the analyst should go back and revise the parameter settings. We can also see the example down here where the clustering actually is not compact at all, so that should not be considered as a useful clustering result. Quickly, as a discussion and outlook for future work, as a future work we plan and already implemented some extensions for the MDS projections, so we can not only show singular plots, but we can encode additional information into the MDS projection. So for example, what the compactness of a cluster to quickly see whether an extracted cluster is compact or not. And we can also encode some kind of ground truth information into the MDS projection. Furthermore, we so far relied on the MDS projection as perceived by the user, but the main problem is that the MDS projection often does not actually show the actual distances. So we should also work on the quality assessment to show whether the MDS projection itself does make any sense. And finally, also some experiments with other projection techniques like TSNE or other distance-preserving quality measures. So finally, our tool should in the future support also feedback, that the user can change parameter setting and immediately see the results in the projection, compare multiple results, and also apply this visualization to related approaches. For example, subspace nearest neighbor search, where the idea is to search not for nearest neighbors in the full dimensional space, but rather search for different nearest neighbor sets in different projections. With this slide, I would like to thank you for your attention, and I'm happy to answer any questions. Thanks.
Okay, thanks, Michael. Questions?
I just wanted to ask if you use any text data sets? Like, did you do any clustering with text documents?
So we didn't apply that to text data so far. So what we did is, so basically the framework allows you to upload any kind of clustering result which you can compute with your algorithm. So what we did, we combined that framework with the Open Subspace project, which is basically a VK extension for subspace clustering results. And in the Open Subspace project, there is one paper describing what is for multiple different data sets, what is the best clustering algorithm with the best parameter setting. And for the examples which you have seen here, we basically took the best quality, so the best clustering results for different data sets and parameter settings, and we can see that that very good clustering results based on the evaluation in the Open Subspace projects still provide some kind of information that the clustering result is not good or not very good. Does that answer your question? Okay. Yeah.
Okay, another question. Yes, all the way there.
Hello. Can the framework incorporate output labels, for example, in multiple labeled problems, or is it specific to only inputs that you're wanting to cluster?
So it's basically. Sorry, I didn't get the question completely.
So I guess I'm trying to see if this framework could help us visualize good clusterings for when you do have output labels available to you.
Okay. So so that is not part of the framework yet, but that is like, especially if you have ground truth information, you would like to encode that into the visualization itself. So it's not supported yet, but we already have plans to encode that information as ground truth into the MDS projection, or also to kind of like compare your results with some kind of ground truth label. So maybe we can catch up after the session and discuss about like possibilities. Thanks.
Okay, let's thank the speaker and